All right, we are in Module 1, Topic 3. This is Lesson 2, Proving Triangle Congruence. So we're basically just trying to prove that triangles are the same or congruent to each other. All right, so for the warm-up, you can see here that we're just trying to figure out how to map figure A onto each of the other figures. So to get from A to B, we see it's a translation down, and then to get from A to C, it flips or reflects over this vertical line, and then to get from figure A to figure D, it's a rotation 180 degrees. Our learning goals for this lesson are using the definition of congruence in terms of rigid motion to show that two triangles are congruent. We're going to be using the side, and side angle congruence theorems using rigid motion transformations. And here are your key terms. All right, our essential question is how can you use isometries to prove congruence theorems? All right, now for the getting started, you can see that there are these two triangles. So I went ahead and measured already. So I measured AB, and that gave me 1 1/3 inch. And it was the same thing for NR. So these two are congruent. And then AC and NL were congruent, and I got that measurement down here. It was 5/8 of an inch. And then BC and RL were congruent. That gave me 1 5/8 of an inch. And then for the angles, the corresponding angles are indicated here. So angle A and angle N are corresponding and congruent. Angle B and angle R are corresponding and congruent. And then of course C and L are corresponding, meaning they're the same angle. They're in the same spot in each triangle basically, and they're congruent. So for activity 2.1, we're just going to be looking at congruent line segments by reflection. You can see this right here. So congruent line segments and congruent angles are often denoted using special markers rather than given measurements. So a slash marker, let me highlight that. So a slash is for congruent line segments, whereas an arc marker is for congruent angles. And you can see down here, these two angles are congruent because they both have the same arc marker. These two angles are congruent because they have the same arc marker. These sides are congruent because they have the same slash, and then these sides are congruent because they have the same slash. And then right here, we can just write the congruence statements. So we can see that angle R is congruent to angle W, and then angle, what is this, WXB is congruent to angle RTS. And I wanted to use 3 letters for these two angles because angle X could refer to this angle or this angle, so we want to be as specific as possible. And then for letter B, we have angle TDM, so angle TDM. And I'm using 3 letters again because it could be this angle or this angle, so we want to be specific. Angle DZC. And I forgot I need to use the little arc mark so nobody thinks this is a less than symbol. And then these two sides here and here are congruent, so segment TD is congruent to segment DZ. And that's how we can use the markers. Next page. All right, so don't forget that isometries preserve distance and angles. All right, and here's just a worked example talking about you can use 2 reflections to get one line segment to another congruent line segment to map it on there. And so you can see what they did here. Okay, the proof in the worked example shows 2 reflections create an example which AB maps onto CD in just one reflection. So if I draw the reflection line like here, for example, you could draw it anywhere pretty much, but if I draw it here, then I would just want to reflect. You know what? I'm going to use the same color. I would just want to reflect. So I'm going to draw perpendicular lines. And I'm using vertical and horizontal on purpose because in Notability, it's easier to see. It's easier to create horizontal and perpendicular lines. So it needs to be perpendicular and equidistant or equidistant. So that would be D. So I'm just making the same distance on both sides here. And that would be C. And there you go. So, oh, I'm going to do that, sorry. So there you go. All right, keep it pushing. Now we're going to take a look at the first theorem, which is the side-side-side congruence theorem. Okay, so we're going to be proving that triangles are congruent given different minimal criteria. So the first minimal criteria is using the side lengths only, not the angles. So we have these two triangles right here. We see that VA equals, so just this right here. VA equals BK. And VR equals BF. And AR equals KF. All right, so complete the steps to show the proof that these two triangles are congruent. So we could do what we did in 2.1 and basically show two reflections that would map this triangle onto this triangle, all right? Or you could just use patty paper to prove that these two triangles are the same. We know that the sides are the same, but we're trying to figure out, are the angles also going to be congruent? And if that's the case, then the triangles are congruent to each other, okay? So side, side, side is just saying if you have three pairs of corresponding congruent sides between two triangles, then the triangles themselves are congruent. The angles will also be congruent if that is the case. Okay, so summarizing the proof in question 1, explain how knowing the three corresponding sides of a triangle are congruent proves that the triangles are congruent. That's just it. The side congruent theorem states that if three sides of one triangle are congruent to the corresponding sides of another triangle, then triangles are congruent. Okay, that's all you need to know. All right, if two triangles are congruent, then each part of the triangle is congruent to the corresponding part of the other. We call this CPCTC. Corresponding parts of congruent triangles are congruent, or CPCTC. Basically, if this is true, this is what I was saying. If this is true, then the angles are also congruent, even though this has nothing to do with the angles specifically. All right, write congruent statements for all corresponding sides and angle relationships of the pre-image and the image. So we got, I'm gonna just do it up here because I don't feel like going back and forth. So we obviously know the sides, and that would be AV is congruent to BK. Actually, no, I don't like that. So if we go from A to B, that means we need to go from K to B. It has to be in the same order. Well, it should be in the same order. And then VR is congruent. So V to R, B to F. I'm using the arrows just to figure out what order that I need to go in. And then RA is congruent to FK. So that's all the sides, and then the angles. Oops. The angles. So it should be kind of, well, maybe it's a little tricky, so just be careful. But once you got this, you should be able to figure out that those two angles go together. So angle A is congruent to angle K. And then angle V and angle B. And then angle R and angle F. Next, we got side, angle, side. So that was side, side, side. If all the sides are the same between the two triangles, then the triangles are congruent. All right, side, angle, side. All right, so here in this worked example, it shows, okay, never mind. It shows us, and it should have all the parts already marked, excuse me. So CN and VR, they are already marked. And then we have CF and VM, that's already marked as well. And then angle C and angle V. So here you can see we got two sides that are congruent, or a side in each triangle that are congruent to each other. We got another side, so that's the other side, and then we have an included angle. That's the angle between the two sides. All right. I'm just gonna keep it pushing. Okay, so now we're gonna look here. The side angle side congruence theorem states if two sides and the included angle of one triangle of the corresponding triangle, if two sides and the included angle of one triangle are congruent to the corresponding two sides and included angle of the second triangle, then the two triangles are congruent. So consider this, so let me try to break this down. Consider this diagram. It already tells us that A, B, and D, E, and you can already see that they are marked, so we didn't really need to highlight it. A, C, and D, F. And then we have angle A and angle D right here and right here. So included angle. Angle B is not included because as you can see, it's not between the purple and blue lines. Angle A is included because it's in between. So let me write that down. Included means in between. So that's what we mean. It's in between. So we're going to prove that these two triangles are congruent. Well, I'm going to just keep it a buck. We know that these are congruent because of the side angle side congruence theorem. So because AB is congruent to DE and AC is congruent to DF, and angle A is congruent to angle D, and I'm going to put in parentheses, those are the included angles. Then triangle ABC is congruent to triangle DEF by the side angle side congruence theorem. All right, so now that we know that the triangles are congruent, we can use CPCTC to prove that all the parts are congruent, not just the parts that we highlighted. So we already know that AB is congruent to ED. Did I do that in the wrong order? Yes, I did. DE, sorry. We know that side AC is congruent to DF. And we know that BC is congruent to EF. And then for the angles, we know that angle A is congruent to angle D. We know that angle B, is congruent to angle E. And angle C and angle F are congruent. All right, 2.4, angle side angle, congruence. All right, so for this one, we are considering that FG is congruent to PQ, and G and Q are congruent, and then angle F and angle P are congruent. And we're trying to prove that these two are congruent. So obviously you can use patty paper to draw on one, to trace one, and then put it on the other to see if they are congruent. Okay, so for here we got the angle side angle congruence theorem. If two angles and the included side of one triangle are congruent to the corresponding two angles and the included side of another triangle, then the triangles are congruent. Okay, so for this one, we have an angle that's congruent in both, another angle that's congruent in both triangles, and then the side is in between those two angles that we highlighted. So don't forget, included means in between. So this side is in between. So when it says the included side, that's what we're saying. Write the congruence table for all corresponding parts and angles. I'm going to do that up here so I don't have to keep scrolling back and forth. So we already know that FG is congruent to PQ. I'm just copying from the given information. All right, so that was FG, and then GH is congruent to QR, and then HF is congruent to RP. And then for the angles, we know that angle G is congruent to angle Q. We know that angle F is congruent to angle P. And that means angle H is congruent to angle R. So we'll just copy and paste that. Cut and paste. All right, so those are the three theorems. So non-examples of congruence theorems. So again, just to remind you, these are the three theorems that we just went through. All right, number one, Juno wondered why angle isn't on the list of congruence theorems. Provide a counterexample to show him why it's not considered a congruence theorem. So I'm just going to start by drawing an example. I'm going to take this, I'm going to duplicate it so you see that that's the same exact triangle. Now I'm going to do this. Okay, so I know that you are tempted to think that, and when we say AAA, we mean angle, angle, angle. But I know you're tempted to think that these angles are not the same. But look, yes, they are. They're equal to each other. These angles are also the same. And again, look, they match up. They are the same size angle. Just because the shape is bigger does not mean that the angles are. The angles still got to add up to 180. All right, if I have to do it a third time, then I shall do it a third time. Boom. So I did all that to prove that these two triangles, have the same size angles. They are congruent. However, these are not congruent triangles. So the triangles are not congruent, even though their corresponding angles are congruent. All right, so Juno wondered why side-to-side angle isn't on the list of congruence theorems. Provide a counterexample. So I just quickly found this counterexample. So SSA will not always create a unique triangle, and here's an example of why. So you could have this triangle right here, which has an angle, a side, and a side in that order. And then you can have a triangle like this, or you could have the original triangle. As you could see, that 6 segment, that side length, the side with the length of 6 could attach here, or it could attach here, and it would still fit the qualifications of side with the angle. So there you go. All right.